So it is great pleasure to have B. Ravinder from IIT Tirupati with us. He will give us some chapters on the uh, more subtle theories on the Lie algebras. So I request him to begin his lectures. Actually, so B.
Uh,
Ravinder.
thank, yeah, thank you, Sachin and Amit for giving me this opportunity. So my goal is to discuss about representation theory of uh, finite dimensional semi-simple Lie algebras over complex numbers. So Shraddha already introduced the representation notion, but let's recall. So what is a representation of G? It's a tuple. You need a vector space and you need a map. Right? So what is V? V is a finite dimensional or any vector space over C, and rho is a map from G to GLV. So GLV is a Lie algebra, and because it's associative algebra, so this is a Lie algebra homomorphism. Okay, so Lie algebra homomorphism means it's a linear map and it respects the Lie bracket. So the Lie bracket notation for G is this, and GLV is a commutator. So rho of x compose rho of y minus rho of y compose rho of x. And equivalently, so the G acts on capital V. So V is a G module. So what does that mean? There is a map from G cross V to V. So that map I'm denoting by x dot V. See what is rho is doing there. So rho is so rho here. It takes a element of G and it produces a linear map from V to V. That means it takes a vector. So it takes a vector and associates another vector. So this you can think of as rho of x acting on a vector gives another vector. So if you fix x, and the rho of x can be thought of as a map from V to V. So here as well, that's what is happening. So the properties which are there here, so equivalent to the properties here are you want rho is linear. So that means this map should be linear in the first coordinate. And rho of x is an element of GLV. If you fix x, that tells you that GLV is a linear map from V to V. That tells you that this map should be linear in the second coordinate. So that is called bilinear map. So this is a bilinear map. And the last property we need is this. So that tells you that if you act with this, is same thing as okay. So this is the definition you have seen already, and my goal is to classify all finite dimensional representations of semi-simple Lie algebra G. Okay, up to isomorphism. So this isomorphism is what do you mean by an isomorphism of two representations? So it is like they are same space. They look different, but they are same. Like only the symbol. So the W is a dummy copy of V. So if that means just I denote, let's say, basis like V1 to Vn, and the basis of W1 is W1 to Wn. So just the symbols are changing. So there's an isomorphism. So it's a linear isomorphism. So isomorphism of representations means the vector spaces should be linear isomorphism. So basis should go to basis. And how X acts? So X, let's say, suppose here X is acting and moving to V3 under X, and V3 is going to W3. So X should act in the same way here. So that's what W1 should go to W3. Means in V and W, the elements look different, like VIs and WIs you're denoting, but the action is also same. So what is the action is same means, if you want the action of X on W1, how are you getting the X on W1? So W1s are images of pi of V's. So that X of W1, you get it from, you go back to V1. So you go back to V itself, then acts X, you get V3, then you take the image. So this is it preserves the dot action. So the map pi should be preserving the dot action. So, and then there is an bijective linear map is there. So it's an isomorphism. Isomorphism is basically the vector spaces look different. It just means the symbols are just changing. It's V1 is just the notation change, but everything else is same. So you don't want to study them differently. That's why you club them and study. At least, yeah. If you study V, you can study W. So, and in this way, you already did. So I think this. So first example, I think G semi-simple Lie algebra. So example to keep in mind is SLN C or SLN plus 1C. So trace zero matrices, n cross n trace zero matrices. So I want to classify all representations of SLN also in particular. So SL2 you have seen already. So what you have seen from Shraddha's lectures that finite dimensional irreducible representations of SL2C are actually corresponding to non-negative integers. So this is this you have seen in the beginning of the lectures of this workshop. So how they achieve this? So I want to do the same thing here, whatever this method is. So how Shraddha did it. So I want to use the same method to classify all the representations, not only SL2, I want to replace it with semi-simple Lie algebra. So what is the method she has taught? So you take a vector space V. The first thing is, how do you associate a non-zero, non-negative integer? Right. So what is the step one? V is given means rho is given from SL2C to GLV. It's a linear map is given. Then don't look row entirely on SL2C. Just look at the matrix H she denoted, namely 1, 0, 0, -1. So just look at row H as a map from V to V. And this is a complex vector spaces, finite dimensional. So it has an eigenvector. So there exists a an eigenvector V in capital V of rho H. Right? So this eigenvector, by definition, if you act with h of v, some eigenvalue, it will be mu. Let us say it's a now complex number, mu v. Some eigenvector exists. So that's the first step. You no need to look row entirely on SL2C. You restrict it to some diagonal matrix, namely H. That is one diagonal matrix. So then next step, keep hitting with ease. So SL2 actually has H is there, but there is a E, there is a F. So E is upper triangular matrix and F is lower triangular matrix. So SL2 has a nice basis given by these three elements. And this is a notation she used. And after getting that V, one eigenvector, you keep hitting with ease. So the next step is keep hitting with ease on V. So what is this hitting will happen? So if you have a weight space V, then if you act with the E, that weight will increase by 2. That's what she did. And if you act with F, this is in weight mu, so the weight will increase. F will reduce the weight by -2. So if you keep hitting with E, so the weight will keep increasing and increasing and increasing. And they are all different eigenvalues you're getting. So because then there will be linearly independent corresponding, because the eigenvectors corresponding to distinct eigenvalues. But because capital V is finite dimensional, so there will be some vector with eigenvalue lambda. So such that if you act with E, it will be 0. So if they, right, so if everywhere non-zero you get it, keep hitting, then you get infinitely many linearly independent vectors. You don't want that because you are in finite dimensional setting. So you are able to find a vector which kills by E, right, and which is an eigenvector. So V is in V lambda means that H act as some scalar. It is at present complex number, right? And if any vector satisfies these two conditions, is called highest weight vector. Highest weight vector, okay? In the SL2C setting. And so this is the highest weight vector she looked at. And then finally in third step, she proved that even that lambda, whatever complex number, is in fact a non-negative integer. And she tried to associate to that lambda. So here, so lambda she associated as a corresponding to a weight of an highest weight vector in capital V. And after getting lambda, so then you keep hitting with F. So the fourth step is you have now V lambda vector. You keep hitting with F's in certain times. Then the next time it will be 0. So in fact, it is proved that you can hit with lambda plus 1 lambda times. And lambda plus 1 times, if you hit it, it will be 0. So this is a spanned by, so this is a basis in fact for capital V. Because V is irreducible, so this is a sub-representation. So she proved that it is actually a representation, means it is preserved by the, so this entire thing will be a SL2C module. It's preserved by H action, F action, E action also it preserved. So it is a sub-representation and V is irreducible. So V equal to this. So this is the same thing I want to do it for in general for any semi-simple Lie algebra. Okay. So before going to semi-simple Lie algebra, so just begin for SL3C. Okay. So I want to do the same thing for SL2C, SL3C. So I have a irreducible representation, right? So V is finite dimensional irreducible representation of SL2, SL3C. That means there is a map from SL3C to, so the question now is, what do you associate to it, right? So that's a question. So to find that lambda, what you need to do, you restrict. So you no need to now study rho on entire SL3C. You can restrict it to one diagonal matrix, but you don't get enough information about the row. So you collect all the diagonal matrices or any two diagonal linearly independent diagonal matrices. So I mean, so which is equivalent to all diagonal trace zero matrices. So all diagonal trace zero, they lie there, so they are not now belongs to. So instead looking one vector, if you want to extract more properties of row, you restricted your study of row to these all diagonal matrices Then when you restrict it to all diagonal matrices, so this is a collection now, collection of all linear maps where they sit in GLV. And what are the properties of this collection? You know, all diagonal matrices are commutes. So the Lie bracket preserved by rho. So all the elements here pairwise mutually commute. So they have pairwise commuting matrices, commuting linear maps. So when you have a pairwise commuting linear maps, it is from linear algebra. So, you know, if you have one matrix, there is an eigenvector, you know. If you have many matrices, even infinitely many matrices, but they're all mutually commuting, they have a common eigenvector. So this is an easy observation from linear algebra, which tells you that there is a vector V, which is a common eigenvector for every element of rho h. So for every element of rho h. So it's just do for two cases, then you will come to know how to do for other cases. So any commuting matrices we have, they have a common eigenvectors over complex numbers. Okay. Now I got a common eigenvector. So this is the same thing of weight mu, let us say. So weight mu. So what is the weight mu means? Whenever h acting it, it's not only one h now, there are bunches of h's, right? So there are many h's in all diagonal matrices are there. So the eigenvalues are encoded now by, they are scalars, so they are depending on h. So you write as mu of h and v. So for all h in, for all h diagonal matrices, right? So this is actually the notation for v mu. So this is called weight space. You are collecting all the vectors, which are all eigenvectors of weight mu. Weight mu means mu is now not a, so it's an eigenvector. V is an eigenvector, but corresponding to an eigenvalue mu of h. So each diagonal matrix gives an eigenvalue mu of h, right? So you want to collect it. So that mu, if you observe, it's actually giving an association for all diagonal matrices to some eigenvalues. So in fact, it's an observation that if you take sum of two diagonal matrices, h1 plus h2, and because this dot action is linear in the first coordinate, so you get that in fact mu is a linear map, means it belongs to h star. So the eigenvalues here now, they are not scalars because you are restricting to many diagonal matrices and they have a common eigenvector. So that vector is V. That vector will be V. Its eigenvalues corresponding to each h, they will be different. That's why you will get different complex numbers. So the eigenvalues now are elements from, so each h there is a complex number. It's an easy observation that it's in fact a linear map mu is. Okay. So given so now this is one eigenvalue, you got it, but one eigenvector you got it. Then keep on hitting. So I want to do the same thing now. You keep on to the step 3. Once you got a common eigenvector, now you keep on hitting with the upper triangular matrices. So SL3C will be direct sum with upper triangular matrices. So this is upper triangular. Maybe the notation is n plus. Then there is a n minus. So this is upper triangular. This is lower triangular. Now what I do, I keep hitting with, so the step thing is keep hitting with upper triangular matrices to that V, which is a V mu, to that common eigenvector. then because of the same reason, so you get that there will be some vector which will be killed by, so there exists some vector v, now say lambda, which will be killed by all the upper triangular matrices, which will be killed by all upper triangular matrices, all upper triangular matrices. Kills this vector. So it is now what you do, and this you call as so that means, what is that means? It's an eigenvector, and all upper triangular matrices will kills it. So the notation by, yeah, how do you denote? Okay, so okay, so maybe let's note later when I do for the entire G. So you have so this vector is called highest weight vector. So a vector which is an eigenvector for all diagonal matrices and which is killed by all the upper triangular matrices, it is called an highest weight vector. Once you have the highest weight vector, then you keep hitting with Fs. So keep hitting with lower triangular matrices. To this V lambda, this V to this small v. Somehow you should get entire capital V. And even that lambda should have some nice properties. So the lambda should belongs to not in H star, maybe with special properties. So that element I want to, that is the correspondence I am looking for. So here, here it was in C in the beginning, but it is a very special that it lies in non-negative integers. So that lambda will be of special property, and that is a set I am looking for now to the right side. How do you correct? So for the correspondence, that is a set I am looking. So I want to do the same setting now for any semi-simple Lie algebra. Okay, so any semi-simple Lie algebra I want to do it. For that purpose, I need something analogous to diagonal matrices. I need something analogous to upper triangular matrices. I need something analogous to lower triangular matrices. Right? So this triangular decomposition I need for any semi-simple Lie algebra. It looks like it has not covered till in this program. I'll just go through about it. I need it. So for any semi-simple Lie algebra, I need this. This is this triangular decomposition. And using that triangular decomposition, I want to mimic the same thing and try to get try to prove the classification. Okay. To get the triangular decomposition, so I need some more properties of this rho h. So I need this some properties. This is actually, if you look at this rho h, pairwise commuting is okay. That's correct. And can we also tell that I know H is diagonal, H is diagonal matrices. It contains diagonal matrices. So I think the fact which is not covered here is rho of H is also have all diagonalizable matrices. So this is something extra I needed to get this triangular decomposition, and I'll go further. So I'm using, so I don't need one vector. So there are many eigenvectors exist. So this diagonalizable is something, it comes from the means diagonalizable elements acts diagonalizably if on a representation, finite dimensional representation. This is a preservation of Jordan decomposition, which I'm assuming at present. So I'm assuming a statement that if I have a representation, so maybe I'll highlight the statement I'm assuming. If I have a representation of any semi-simple Lie algebra, in particular SL3C, because then there is a diagonalizable matrices here, nilpotent matrices here. Then look at the images. The statement is they will be diagonalizable in GLV, they will be nilpotent respectively in the GLV. So this collection row of H, what you are looking here, so the collection row of H, whatever you are looking here, it should be also diagonalizable matrices. So once you have a diagonalizable matrices, you can no need to tell, so one eigenvector exists. It's much more happens. So what you can tell, because this is diagonalizable and they are pairwise commuting, right? So if you have two diagonalizable matrices, if they pairwise commute, they simultaneously diagonalize. What is the meaning of simultaneously diagonalizable? So the V has a basis with common eigenvectors. So it has a so the eigenvectors now are corresponding to, as I told you, they are common eigenvectors. So they corresponding to H star. Okay. So not only one eigenvector exists, there will be, if a dimension of V is n, there will be n eigenvectors exist. So this is not true for nilpotent matrices. I'm using the fact that diagonalizability. You do get a basis for V consisting of eigenvectors because of diagonalizable. Because the pairwise commute, there's a bunch of matrices are there, all the eigenvectors will be simultaneous eigenvectors for everything. So the eigenvalue is now an element of H star. Okay, so this decomposition, I use it to get the triangular decomposition.
I have a question.
Yeah, please.
Yeah, can you kindly explain once again how did you show that one element in row H is I mean there exists one element which is a diagonalizable?
No, I'm not telling there exists one element which is diagonalizable. I'm only. So are you asking about? Are you asking about this statement? No.
No, I'm not asking that. You said
so
that
yeah, correct. So this is a fact I'm using. So this diagonalizability is this is a fact. All the elements in this row of H will be diagonalizable. This is a fact by preservation of Jordan decomposition. So that's what I'm using, a fact telling that a diagonalizable elements in SL3C. If you look at any representation row, you take it, you look at its images, they will be diagonalizable here. Okay, so I'm using it as a fact. It will be there in Humphrey's book, beginning, even 6th chapter, before SL2 representation. So yeah, preservation of Jordan decomposition theorem is there. So you can look for, so diagonalizable elements goes to diagonalizable, nilpotent elements goes to nilpotent elements. So it's a fact I'm using at present to get this decomposition. Is it okay?
Yeah, thank you.
So so what I got at present now? Now I got a weight space decomposition, right? So this is a weight space decomposition. So this decomposition is called, so maybe I will, so whatever I did so far, so what I did here, maybe I'll note down. Please.
Actually, whether it is true for all representation or any output like
it is true for any representation, but the thing is, this is semi-simple is needed. The Lie algebra is semi-simple. There you can talk about nilpotent elements and diagonalizable elements. Here SL3C, they're matrices, so you know it's nilpotent means. But semi-simple also, you know what is a nilpotent. So there's a definition. We'll see that. Yeah. So for any semi-simple Lie algebra, you take a diagonalizable matrix. That image will be diagonalizable for any representation. The only thing, finite dimensionality is needed here. Is that okay? Any other questions?
Okay.
Okay, so maybe I will. Okay, so So I think a special case. Let's try for so G is semi-simple Lie algebra. Let's restrict our case to adjoint representation. Right. So I told you that for any semi-simple Lie algebra, for any representation, you can talk this, right? So that's what I'm in fact taking adjoint representation, which is a map from G to GLG. Right. What adjoint representation will do, by definition, it takes a vector, it associates to add x, which is a map from G to G, which this is using the Lie bracket, you can define it. This is adjoint representation. You have seen it. This is one of the examples of representations because it's a representation because I think it's using the Jacobi identity for Lie algebra, you can prove that it's a representation. So this is called adjoint representation. Now, what is the notion of semi-simple element here? What is the notion diagonalizable element here? So I told you that diagonalizable elements, what is the meaning of that? And what is the meaning of nilpotent element? So the definition is you look for add G. So by the way, so I think what is analogous to the, so maybe the notation now. So what is semi-simple? So X in G is diagonalizable or semi-simple, diagonalizable element or a semi-simple element. That means if you look for the add X, because I know for matrices or linear maps, what is a nilpotent, what is a semi-simple, so what is a diagonalizable? So it should be add X is diagonalizable. So how do you define the diagonalizable elements for any semi-simple Lie algebra? You look for add X. So that should be diagonalizable because it's a linear map, I can talk. And then X is nilpotent if add X is nilpotent. So this is the definition of nilpotent and semi-simple elements. And the fact of preservation Jordan decomposition tells you that if you restrict this map, add map, you have from G to GLG, but you have to restrict it to something like a diagonalizable matrices. So means in SL3C, I restricted to all diagonal matrices. So what is the property of all diagonal matrices here? It should be every element should be diagonal or diagonalizable here. And pairwise commute. So H has a property. If you see the diagonal matrices for SL3C, they have a property that every element is diagonal and pairwise commute. That is the meaning of abelian Lie algebra. What else you need? So you take it maximum with this property so that you get more information. So maximum subalgebra, maximum abelian subalgebra. So that abelian is taking care of this pairwise commuting. So that I can keep in bracket because there's abelian. And then the more important thing is every element should be semi-simple or diagonalizable. Right? So in SL3C, if you collect all diagonal matrices, they have this property, and that is the maximum with respect to this property. Okay, it's an abelian subalgebra such that every element is diagonalizable. Means so such subalgebras exist. So this is also because G is semi-simple Lie algebra. They are called, so first of all, such subalgebras are called Cartan subalgebras. What is a Cartan subalgebra? It is maximum abelian subalgebra consisting of all the diagonalizable elements. Okay, and that is called Cartan subalgebra. And such subalgebras exist for semisimple Lie algebras. So this is all. So if you're not clear what is happening, you restricted yourself to G is SL and C. This is all diagonal matrices. Stage 0 diagonal matrices. Take all diagonal matrices so that you get more information. So the fact just now I used is you look at for that image. This sits in GLG. But what is that observation is telling? This is the preservation of Jordan decomposition telling is this set as pairwise commuting is okay because of the Lie algebra definition. H has that property, so H is abelian, so add H is abelian. Pairwise commuting, and what else? And they are in fact diagonalizable or semi-simple. So this is the fact I'm using. Because if you have a representation by preservation of Jordan decomposition, if you have a representation of semi-simple Lie algebra, diagonalizable elements image will be diagonalizable. Okay, so this is great so far. So you have what is the setting now? Pairwise commuting diagonalizable matrices. So you try to do the same thing. So this implies G is simultaneously diagonalized, means you are able to write some eigenspaces will come. So alpha is in H star, right? So what is the G alpha? G alpha is eigenspace, means you take the elements. So such that with eigenvalue, if you act with add H, so add H of X is Hx. The eigenvalue is a different H, different scalars. So then X is an eigenvector. So this is the right? This is called, so this is supposed to be weight space earlier. So what we are calling now is, this is called a root space. This decomposition, whatever you are getting here. So this is, so whenever alpha is in H star, for G alpha is non-zero, then such alpha is called a root of G. And if you collect all those alphas where G alpha is non-zero, and by the way, the zero, so you may have to remove that so the zeroth, because root system definition, this is a root system. So just y zero you have to remove. So by the way, if you look at for z0, what is the definition of g0? So ask the question that is zero functional, is an eigenvalue or not? What is it telling? It is set of all vectors such that if you apply with H, it should be 0 for all H in H. What is G0? It actually, it has all the elements of G which are commutes with H. And do you have any such elements which are commute with all the elements of H? So if you go back to your SL3 example, do you have, so what is the question here asking? So those elements in SL3 which should commute with all the diagonal matrices. Do you have such elements in SL3 which are commutes with all the diagonal matrices? Right. So in fact, all the diagonal matrices will commute with all the diagonal matrices. So definitely every H is there. So because it's Z0 is non-zero, so it should also called as a root, but your root system doesn't allow root. So you take alpha is non-zero. So then only you call as a root. So and you do you remember that what are all the matrices which commutes with all the diagonal matrices? So they are in fact only the diagonal matrices. So what you have observed that diagonal matrices have this property, they commute with all the diagonal matrices. But moreover true is only these are the matrices which commutes with all the diagonal matrices. So in general also true, here also true. So finally what you are getting, G can be decomposed as some Cartan subalgebra you begin with. Then there are some root spaces which are coming from root system. Okay. Now, so what we did at present, so maybe it's better to do in this example, G is equal to SL3C. Okay. Or is it, so this decomposition is called root space decomposition. Slowly, I am going towards what is my goal. For SL3C, I know this is set of all diagonal, so maybe I will. So for SL3C, this is all diagonal matrices. There are some upper triangular, there are some lower triangular are there. Right. So in the root system chapter, which is given by Sachin, you know, this all root system can be classified to some positive roots and negative roots. So those corresponding to positive roots are analogous to the upper triangular matrices. Corresponding to negative roots are analogous to the lower triangular matrices. So slowly I am getting the triangular decomposition for any semi-simple Lie algebra. Okay. So that's what my goal at present for some time. So because that upper triangular matrices, I need it to hit with the highest, to find this highest weight vector. Okay. So even if you restrict my case to G is equal to SL3, you take all the diagonal matrices. So maybe let's yeah, you need this. I think I need to explain this because some more properties of roots I need it, which I motivate by this example. Okay, so H is all diagonal matrices, trace 0. What you did, you have to look for add H, which is actually in GLG. So the thing is, how do you find the root space decomposition for this G? So even this you can erase. So the question now is SL3C. I know I can write it as all diagonal matrices, right? Then there is some upper triangular matrices. So upper triangular matrices, I'm taking a basis, which is E first row, second column. Right. So this is the by notation for this is 0, 1, 0, 0, 0, 0. And then E1, 3 or E2, 3. Then E1, 3. Then there is corresponding to, there are some lower triangular matrices. So my goal is to show now is this usual vector space decomposition, in fact, the root space decomposition. So what I mean by that, this one, is it a common eigenvector for all the these vectors, right? So these vectors, even left hand side, will be the common eigenvectors for the action of H. Okay? So is it true that, so if you, so is E12, is it an eigenvector corresponding to the all the diagonal matrices, especially diagonal matrices has a basis, and namely this has a basis, right? So 1, minus 1, 0. And then it is a two-dimensional, so there may be, this is a basis. So H has a basis. So if you want to check an eigenvector for all the diagonalizable, all the diagonal matrices, enough to consider this basis. That's why in SL3C, it's enough to consider these two basis elements. In SL2C, you have only considered one basis element, but in SL3C, you have to consider these two. And that I'm denoting as E11 minus E22. So if you do this product, you all know how do you multiply EIJEKL, this is an easy observation that it gives something only when j is equal to k. So it gives something when j is equal to k. So if you multiply this, when 1 is equals to 1, I get E12. That is a product AB. Then I have to do BA. Then there is a 2 here. This 2 and this 2 will give you something, but this doesn't give anything because there is a 1 here. So then there is a negative sign is there. So plus E12, which is 2E12. Right. So what you are observing here is, so this is like a H1. This is like E1. HE1 is 2E1. Right. So these relations, these relations you have seen in SL2, if you remember. And then maybe one more thing, you need a functional, right? So what is this alpha? So this is equals to E12 is equals to a root space corresponding to some alpha. What is that alpha? How do you find that alpha? Alpha is a functional. So the eigenvalue, what you get alpha is now, this is an eigenvalue. So alpha I supposed to define from H to C. On first basis vector, the eigenvalue should be 2. On second basis vector, what is the eigenvalue here? So let's try the second basis vector, E22 minus E33. Then you take the E12, same vector. This is an eigenvector. The eigenvalue will be same thing as, so 2 here. So if you multiply this with this, it will not contribute anything, 0. AB is 0. Because there is a 3 here, there is a 1 here. Then if you multiply BA, this 2 will give you something. So with a negative sign, AB minus BA, E12 you are getting. So the eigenvalue corresponding to here is minus 1. So this first root alpha 1, you are getting as a functional, which takes H1 to 2 and H2 to these two basis elements like that. But if you try to express in terms of these projections, epsilon 1 is a projection to first coordinate. Epsilon 2 is a projection from diagonal entries. So something lambda 1, some D1. So it is the first projection map. These are projections. Means they take something diagonal entries to just first entry. This is a second projection. Then you have a third projection. And if you try to explain alpha 1 in terms of the projections, so this first projection plus, right? So if you write epsilon 1 minus epsilon 2, I'm getting it's matching on the first basis vector. Because epsilon 1 minus epsilon 2 is also take same thing, it's 2. And second basis vector also it is taking 2. 3 doesn't, so this goes to minus 1. So that is also, so alpha 1 is epsilon 1 minus epsilon 2. And whatever here, so this is called as H2, this is called as E2, no, this is E1. But H2 E1 I no need to worry, so this is okay. So similarly, maybe I'm writing it, so for the want of time I just, so my alpha here is epsilon 1 minus epsilon 2. Whatever calculation you did, same thing. If you swapped 1 and 2 to 2, 1, so you get minus of epsilon, so epsilon 2 minus epsilon. Then this is epsilon 2 minus epsilon 3. Same calculation with instead 1, 2, you do 2, 3. This is epsilon 1 minus epsilon 3. So the roots here, what are you seeing the roots? So the roots here are alpha 1 is epsilon 1 minus epsilon 2. Alpha 2 is epsilon 2 minus epsilon 3. Alpha 3 is epsilon 1. So I'm corresponding to E13, it is epsilon 1 minus epsilon 3. And you have seen in root system that if alpha is a root, minus alpha should be a root. So these three are the negative side. And one more beauty is happening here is, so this is the roots and this is the root system for SL3. So all these 6 elements, okay. And one more thing is happening here is each root. So for example here, This is the epsilon 1 minus epsilon 2 is a root. For each root, you take its root space, let's say E12, right? And that E12 here, it is satisfying that H1 E1 is 2 E1. And SL2 relations, if you want to see, so if you want to see SL2 relation, what is that? There should be F1. So the corresponding F1, what property it should have? So H1 F1 should be minus 2 F1. Okay. And it's a easy check that this one, so this one has that property E21, because it's just swapping, so the negative term will commit. So this is a E21. So the thing is, for each root here, there is an SL2 copy. So this is an important fact I need it. So that's why I'm doing this example. So for each root, right, there exists a SL2 copy. So that means there exists a E alpha. There exists in G alpha and F alpha in G minus alpha, H alpha in capital H, such that this is SL2. Right? For example, if I ask you, if someone asks me that if this is my root, what is a SL2 copy? So I take it as E1. If this is alpha 1, my E1 is E12. That's what I have taken. E12. E12 is given by this, right? And E21, that is in the minus alpha. So E21 is F1. And if you do the Lie bracket, H1 should be equals to EF. Right? So the relations, if you remember, there are three relations. One is this HE is 2E, HF is minus 2F. Then EF should be equals to H. So once you do EF, it's equals to exactly E11 minus E22, which is H1. H1 is E11 minus H2. And if you want to see that what SL2 copy it is getting, so the SL2 copy corresponding to alpha 1 is exactly, so you need this E12, right? So E12 is where here. So 0, 1, this is E12, then E21 is here. So it's a lower triangular. Then there is an addition, H1 you have to add. So H1 will become, no, finally you have a linear combination also you have to take. So I think what you get here is some B. So if you do a linear combination, so there is something here. It is A times E1 and this is B times F1 and then C times H1. So this is an SL2 copy which sits inside SL3. So this is like an SL2 copy. Similarly, if you want E alpha 2, which is epsilon 2 minus epsilon 3, the SL2 copy sits below. And similarly, if you want alpha 1 plus alpha 2, the third root, the SL2 copy sits in the, so because if you look for E13, it is E13. What is the meaning of E13? So it is this. And its spanning will be at that corner, and there is lost at the end, it is E31. So it gives the corners. So this corner, then the diagonal entries will be this minus this. So these three are the SL2 copies corresponding to each root. Okay. But if you take another root, still the SL2 copy is same. If you take minus alpha 1, the same SL2 copy you get. Okay. So the more things what you are observing here. So they are all facts now quoting for semi-simple Lie algebra. Okay. So for G semi-simple Lie algebra, what happened? Where it is going? So for semi-simple Lie algebra, what are the facts you are taking? It splits into, it has a root space decomposition. And this pi is a root system. And corresponding to each root, there is an SL2 copy. We denote by SL2 alpha. Now I want to separate as a upper triangular and lower triangular, right? So that's what I want to make it. So if you look this picture, something analogous to upper triangular and lower triangular, I want to do it for any semi-simple Lie algebra. So if you look this picture, this alpha 1, so this here, alpha 1. So these three are the upper triangular matrices. They corresponding to roots like alpha 1, alpha 2, alpha 1 plus alpha 2. So these three you declare as a positive roots. You denote by pi plus, and its negative will be pi minus. Right? If you want this to be upper triangular has a means if you want similar to upper triangular and lower triangular in SL3, but this is not the unique way. You have already seen in your root system topic. If you want to see how many ways you can make them this root system for SL3 in terms of positives and negative, as many as number of chambers, as many as number of coordinate of while group, right? So that you have seen it. And if you want to make, if you have one positive root system, let us say, if you act with one while group element, you get another positive root system. And similarly, 6 while group elements are there. You know the while groups in SL3 setting, right? So what is a while group? If you have a root system, you have a while group, which is actually, it's the reflections, right? So what S alpha 1 will do, it takes alpha 1 to minus alpha 1. This is the first property, and then remaining kernel of alpha 1 to 0. That's okay. So if you here in SL3 situation, my alpha 1 is what? Epsilon 1 minus epsilon 2. My alpha 1 is epsilon 1 minus epsilon 2. If you want to make this to minus alpha 1, then it should go to minus of, so what is happening here is 1 and 2 are swapping. So in some sense, so what I'm just not proving, what I'm telling is, so the while group here, so maybe S alpha 1, so while group here, so I'm in SL3 situation, S alpha 1, see while group is that, and also one more thing, the facts, while group actually generated by simples. So what is a simples? So this is all you have seen it. It actually generated by all positive roots, but even all reflections. But then it is it's a proof, it's a theorem that you don't need all the reflections corresponding to the roots. You just take the simple roots, they do generate the while group. And S alpha 1 here, exactly like some transposition 1, 2. S alpha 2 is like 2, 3. And the group generated by 1, 2, 2, 3 is S3. So the thing now is, briefly I'm telling, so the while group in the SL3 setting, it is a S3. And how it acts? So S alpha 1 will take epsilon 1 to epsilon 2. It swaps epsilon 1 and epsilon 2. So they act on H star, right? So they are the elements on, what is the reflection? It's a map from where the root system is lying, right? So this root system is lying in H star. Okay, so where are we? There is a while group there, that is fine. So what I'm telling, as many as while group elements. So there are 6 while group elements are here. So 6 ways you can get a positive, because you just act. you take one positive root system, namely this. You act on this, let's say S1. So if you act on S1 or anything, if you take identity, this is a positive. If you act on S1, what S1 will do, it has to swap 1 to 2. So you get something like this, 1 to 2. So something like this. So alpha 1 is going to minus alpha 1. Alpha 2 is going to alpha 3. And alpha 3 is going to, sorry, it is alpha 1 plus alpha 2. Instead alpha 3, you write it as alpha 1 plus alpha 2. And epsilon 2 minus 1 to swapping, right, S1. So this is alpha 2. So this is another positive root system you can declare if you want. What is the property of actually positive root systems? Every root should be written as either positive integer linear combination of them, and it's negative, so negative integer linear combination of them. So there should be, first of all, there should be some simples in this. So there are two simples here. Can you tell me two indecomposable roots? So what are the indecomposables? If you sum them, you are getting this, right? So this will not be indecomposable, but these two are indecomposable simples. And then its negatives will be, so every root is obtaining like that. Every root is either sum of them or its differences are the remaining root. So like this, you can declare many positive root systems. So for example, this positive root system is here. So number of positive, so one way you fix it. So the moral is fix one, declare something. So you declare pi, fix a chamber or fix a positive root system. There is something pi plus union pi minus, and my G will split into diagonals, then something like upper triangular, so the positive, and something like lower triangle. So this decomposition is called triangular decomposition. Okay. So because we have come so far, so maybe I'll just give a, I'll just connect the dots, means maybe it's connected already. So where are we, what we are doing? So I have a finite dimensional, means because we are different speakers are speaking, so all can be connected now by this small summary. So you have a finite dimensional semi-simple Lie algebra over C. What we did so far right now, so you fixing a Cartan subalgebra which exists for semi-simple Lie algebras, so which gives a root system pi, right? And what is a root system here? Root system usually has some set of vectors, right? So there are some roots, alpha 1, so there are some roots will exist, and also they should be in fact the roots. So the root system pi, you get it lies in H star. So this is the space, but I don't want, see, you studied only the real space. It's H is a map from C to H to C, but root system chapter is studied only for C. So at present you got this pi in H star, but you can take a real span of them. So just to take real span of, in SL3 setting, for example, just to take a real span of those roots. So this is R alpha 1, R alpha 2, and then all other roots. So this is a summation of alpha belongs to pi. You just take all R alphas. So this is actually a real vector space, Euclidean space. You want real space. What is the dimension of this space? With dimension is equals to how many linearly independent roots are there? If you see in the SL2 picture, SL3 picture, so all the roots here are, there are 6 roots here. So where is my 6 roots? Among the 6 roots, only these 2 are linearly independent, or any of the 2, any of the simple ones are linearly independent. Everything is depending on them. So this should span only two-dimensional space, and the two actually coming from H1, H2, they are exactly the dimension of H. Okay, so how many, what dimensional Euclidean space you get it? So it's the dimension is equals to dimension of H. So that's called actually a rank of Lie algebra. Rank of, so rank of a Lie algebra for SL2, for example, its rank is one dimensional, rank is 1. For SL3, the rank is 2, so rank 2 Lie algebra. So you have a root system now, but root system not only needs a real vector space, it also needs a inner product. You positive definite inner product. So the fact is, if you take the killing form is actually a map from where to where. It's a map from H to it's a killing form is there on H actually, but you want a map on this entirely contained in H star, right? So you want an inner product on H star, and it's a so the killing form can be associated. So H and H star can be isomorphic using the killing form. So that killing form is actually a positive definite form. So the killing form gives the inner product. Killing form, which is there on H. So non-degenerate. So that's why you can make it isomorphic to H star, and you can define the analogous form with respect to that isomorphism on H star. So with respect to that form, this is a root system. So this now whatever Sachin discussed, so that theory makes sense now. So you have so what we did actually, you have I'm collecting, I want to know all the finite dimensional semi-simple algebras I want to know. Then you collect all the root systems here, right? But root systems with respect to some choice, some Cartan subalgebra, right? And if you change the choice also, right, you may get a different root systems, but they're all isomorphic. So they're all isomorphic root systems. But what is the meaning of, yeah, okay, anyway, that's so okay, so they're all isomorphic. So the one more important thing is, if you fix a root system, you can go back to G. Every root system, it gives a finite dimensional semi-simple Lie algebra. This is discussed in the yesterday, namely Sayre's theorem. So what Sayre's theorem is telling, given a root system, there are some simples, and using those numbers, that the numbers, right, alpha, j, so these numbers, the Cartan matrix, so the numbers I'll discuss. So there is a Sayre's theorem. Yesterday we have seen that how to construct root systems to a finite dimensional semi-simple Lie algebra. And what you get is, so you begin with a finite dimensional semi-simple Lie algebra, you go to construct a root system and come back here, then whatever you are constructing may not be G, but it's isomorphic to G. So up to isomorphism, semi-simple Lie algebras are exactly bijective correspondings with isomorphic root systems. And this choice is independent of H actually. Then the root systems are isomorphic. So if you want to classify all finite dimensional semi-simple Lie algebras, it's enough to classify now root systems. And this root systems classification is done by Sachin during in this workshop. He has actually each root system, there is if you fix, see, that's what now each root system has a positive and negative things. You have to fix which are positive. The fixing is done by either a while group or fixing a chamber. So what you get is the simples, you get it. So among the, if you get a positives, then you get a simples. The simples gives a Cartan matrices. So the not the simples are important, the matrices are important. What is this numbers? So this matrix, if you remember, the alpha 1 to alpha L are simple, then the matrix has a labeling. So this is alpha 1, suppose this is alpha 2. And correspondingly, there is an SL2 copy I told you, right? So this is H1. This is H2. Then how do you write the matrix? The matrix is given by these numbers. Alpha 1 of H1 is 2 because that's the calculation we have done it. So if you want, because Hx is 2x. So anyway, so this is, so it matrix looks like this, but general entry looks like alpha j of H2. So ijth entry looks like alpha j of Hi. So which is same thing as, with respect to form, it is alpha j Hi by Hi. I hope this is discussed already in this class. So what I want to tell you that these numbers actually same thing as, if you change this while group elements, right? If you take another while group element, then the beauty here is, if you see this, under a while group map, the simples are mapping to simples. These two are simples again, because this is corresponding to some of these two. So this is some of these two. So that's why this is corresponding to some of these two. So the simples are exactly the images of the simples. So this matrix will be same thing under a while group. So this form, whatever you are seeing here, so not Hi here, sorry, this is Hi is alpha I now. So if you corresponding to, if you write only using H star, so because there is no Hi in your root system, I think there is no Hi's. Because so it only this. So this matrix is only this. So this is what you have studied. So 2 alpha j alpha I by alpha I, and this matrix is exactly same. The simples under while group elements goes to simples, and this form, whatever your form, is while group invariant. So this you might have seen it. So I'm also, so what I'm doing now is I'm cutting W because it's independent of choice, fixing the positive roots. You get the same Cartan matrix. The only difference maybe is I'm calling alpha 1 as first, alpha 2 as calling. Someone else may call alpha 2 is first one and alpha 1. So the up to renumbering this alpha is, this matrix is same. And to classify root systems, you have to classify all the Cartan matrices. And by the way, you can go from here to here, you know how to get a Cartan matrix. But the beauty is you can get back the entire root system from these numbers. Because these numbers are given means simples are given. And you know while group is generated by only simples. And you know entire root system you can obtain by while group acting on simples. So just simples are good enough to get the entire root system. And then Cartan matrices are classified by using Lincoln diagrams. So this is a summary you are in, and in fact, what you classified is you classified all the Lincoln diagrams. So even you classified, I think, connected Lincoln diagrams. So the connectedness will give you indecomposable matrices, and then irreducible root systems. You can't write a split into union of two root systems which are orthogonal to each other, and the simple is gone now. The semi-simple now I am replaced with simple. So you no need to work semi-simply. If you want to classify semi-simple Lie algebras, by definition of semi-simple Lie algebra, it's isomorphic to sum of the simple, direct sum of simple Lie algebras. You need to classify all simple Lie algebras. So that's the problem is boiled down to classifying all connected Lincoln diagrams. And you have seen all the connected Lincoln diagrams here. So the connected Lincoln diagrams there are types A and B and C and D and E, F, G, exceptional types. And corresponding to each A n time, there is a representation, there is a Lie algebra, simple Lie algebra, which is the ANs are ranked. So n plus 1 is n rank. B is discussed. So these examples are discussed in first lecture of Shraddha. There, I think, yes, B is orthogonal, special orthogonal with odd. C is symplectic, and D is orthogonal of even. So you means if you connected linkage diagrams on the right hand side. If you want to get the Lie algebra back, you no need to apply the Sayre's theorem for at least for the classical case. You already know some familiar examples; they will be enough. But if you want to do EFG, maybe you have to go to apply the Sayre's theorem and construct a Lie algebra. So that's why they're all sitting in terms of matrices. So all of them are sitting in terms of, so this is a matrix of n plus 1. This is a 2n plus 1 size. So everything is, so they are called classical Lie algebras. Okay. Okay. So this is a connection. So this actually, whatever we did, whatever so far we covered is, we know what are all semi-simple Lie algebras up to isomorph. Semi-simple Lie algebras are direct sum of simples. I know all the simples because I know all the connected linkage diagrams. That's where we did so far. My next goal is I want to classify all representations. So I'm going to representations, right? So so classification of semi-simple Lie algebras, finite dimensional over C is done. So the goal is classification of finite dimensional representations of semi-simple Lie algebra, right? This is the goal. And Wiles theorem, we know Wiles complete reducibility theorem, which is done by Shraddha, which tells you that if you want all the representations, it is finite dimensional. So it will break down into direct sum of irreducibles. And so it's enough to classify all finite dimensional irreducible representations of a semi-simple algebra. And this is where I have this SL2 picture. We did it already. Finite dimensional irreducible representations of SL2C, they are non-negative integers is done. And I want to do it same proof for any semi-simple algebra, and what it corresponds is the question, what set it corresponds. I couldn't do it. I tried the process, same thing like SL2C, but I don't know what is for any semi-simple algebra. What is like analogous to upper triangular and lower triangular. So that's why I did everything. Now I know there is you have to fix some carton. So once you fix a carton, there are some root systems exist. So there are some positives. There are some negatives. G minus alpha, where alpha is positive. So this decomposition, once I know, now I can finish whatever I begin with. So I have a representation. So I have a irreducible representation. Finite dimensional irreducible representation of a G. Now there is so the method is, it's a map from G to GLV. But you no need to look for entire G. It's enough to do over the diagonal or analogous to the diagonal matrices. All diagonal matrices is maximal thing, which is Cartan subalgebra. So if you look for this, V in fact splits into direct sum of weights. So there is exactly one weight vector exists like this. So there exists some V mu, which is in V mu weight vector. That means if I act with all the elements of H, I should get back V mu because it's an eigenvector, but eigenvalues will be depending on H. So this is a mu H. Mu is a linear function. And keep hitting with ease. So keep hitting with ease. I don't know earlier, but now I know. So now I know because I know each G alpha for a positive root. So these are like upper triangular for me. And if you remember, for each G alpha, for each root, there is a E alpha. So G alpha is exactly spanned by E alpha. This I didn't tell you because the dimension of root spaces are all 1. That's also a fact. You have seen that in SL3 situation, only E1, 2 is so the all root spaces are one dimensional. So if you want to hit all the positive root spaces, what your all the upper triangular kind of thing. So this entire thing I want to keep it as a 0. So I'm doing keep hitting with E alphas where alphas are positive. Then the weights will increase. So you should know this easy observation that if you hit with E alpha on a V mu, the weights will increase by alpha. And earlier it is 2 because it is you no need a functional there. You have to take only one vector, which is H alpha, because the SL2 copy is what? F alpha, H alpha. And you have to just evaluate on H alpha. When you alpha of H alpha, if you do it, that is 1, mainly because the main 2, that is 2, mainly because this form a SL2 copy, right? So what is SL2 copy means? E alpha, F alpha, H alpha is an SL2 copy. That will tell you that H alpha, E alpha should be equals to 2E alpha, but by definition of eigenspace, so this is belongs to G alpha, and this is a eigenvector corresponding to alpha eigenvalue. So this should be equals to alpha of H alpha. So, yeah, it's by definition of so alpha of H alpha should be 2. Okay. By definition of eigenvector, root space, by definition, it's an eigenvector for all H alphas. Okay. So keep hitting with E alphas. Where so weights will keep increasing. And also the fact is, if you hit with F alphas, the weights will decrease. Then if you keep hitting with E alphas, the weights will increase and increase. So it's a sort of same argument that you are in a finite dimensional space, and you can evaluate at one point where the eigenvalues are all distinct, namely row check if you want, whatever it is. So basically the same argument will tell you that because eigenvalues are now functionals, not the scalar, right? So yeah, the point I used in the proof that eigenvectors corresponding to distinct eigenvalues are linearly independent. So I am in a finite dimensional, so I don't need infinitely many linearly independent vectors. I can't get it. Here also you can use the same argument by evaluating at 1h. And the fact is, the thing is, you have a weight spaces, keep increasing. So there is some vectors, then E alpha of V mu, E alpha square of, one more time you are hitting it. You keep hitting it. And the weights are now functionals, so you have to evaluate at one h and make them they're exactly some distinct numbers. So this is mu of 2 alpha, 3 alpha. So you can get it where there is some element of h where alpha of h is non-zero, namely h alpha. If you want, you can take it. Oh, but not only one fixed alpha, right? So you keep on hitting with many various E alphas. So it's not only, so you need some element where for all positive roots, one element there exists h. Okay, so this is a while vector or dual while vector, which is row check possible. So if you evaluate it, you get that all have. Anyway, so this is all have different eigenvalues. So the more thing, the beauty here is I'm doing the same process. You try to keep E alphas, you get some weight vector. Weights will keep increasing. So you are in a finite dimensional space. So there exists some vector V mu, V lambda in capital V such that it kills, if you can't act anything E alpha to that. That will be killed by all the upper triangular matrices in sort of. That's what. So this vector is called, such vector is called highest weight vector. This is the weight vector. It's an eigenvalue with a lambda as an eigenvalue. and it kills by all the positive roots. Okay, so what you proved just now is in any finite dimensional irreducible representations, highest weight vector exists. Okay, now you need that condition. The highest weight is exactly the weight actually at present is in H star. You have to boil down to something called non-negative integer, right? That's what my analogy, right? So I have to boil down to, so you remember in SL2, at present, at that time it was in C, but somehow it converted to H0, it's non-negative integer. The argument, if you want to mimic it, she kept hitting with F's. So what I do, so there is some, you can't hit any E alphas. So you try to hit with F alphas. And the thing I got it there is some lambda of H alpha plus 1, whatever it is. So that is whatever here, the eigenvalue corresponding to H alpha is lambda of H alpha. This is lambda of H alpha minus 2. It keep going. But if you hit with this times, this is 0. Because of the, you can't hit somewhere. So yeah, so I think this is, this is okay so far. And this is non-zero. So maybe, so there will be some power, maybe this, so there will be some power. No, by the way, this lambda of H alphas, you don't know so far in means you don't know their integers or not, so you can't hit it. So maybe you have some k, k minus 1, where is it non-zero? And if you hit k times, it is 0. So now you use the fact that you hit with this. I'm done. Only 2 minutes. I'm done. So you try to hit with this. So it is the same proof what Shraddha did it. So I'm recalling the same proof. I'm doing the same proof. The thing she has used here is, if you do like this SL2 calculation here, E's will push back to this side. So what E's will do, E's will push this side. So you're supposed to get this vector with some constant times. So the calculation she has done is, it is k times and lambda of H alpha minus k plus 1. This is a simple SL2 calculation. And this she did it. Okay. And this is 0, I know, but this is non-zero. So this scalar must be 0. So that implies that lambda of H alpha is exactly equals to k minus 1, which is an integer. So what you are getting by this is the lambda, which given a irreducible representation, you have a highest weight vector with weight lambda. Lambda, it was in H star, but right now what you are telling is such that lambda, if you act on all these H alphas, so it should be non-negative integers, because k is bigger than or equals to 1. So this is all. So the correspondence now we are doing is the z greater than or equal to 0 there in SL2 situation. Now also you're getting the similar kind of thing. It corresponds to lambdas, which have the property that on every H alpha, it should be a positive number. And moreover, this should be 0, will tell you that F alpha, k is equal to lambda of H alpha plus 1. V lambda is 0. So there is a vector V. Yeah, this is all at present we are. Yeah. We'll continue tomorrow what to do. Thank you. Thank you.
Thank you, Ravinder. Any questions so far? If not, let us meet at 11:30 for the tutorial session.
Yeah.
Yeah.
So can I stop recording?
Yeah, please.
Okay.